When a monitor speaker fires, it pushes a massive wave of concussive acoustic pressure outward into the room. At the mixing desk, the sound you hear is a composite of that initial signal and the energy colliding with the architecture around you. The primary wave that travels in a straight, unobstructed line from the speaker's tweeter directly to the listener is the direct sound. This reaches the ear first at time 0. This diagram highlights the direct path carrying the raw spectral balance. But because speakers radiate energy in multiple directions, indirect sound waves split off, traveling a longer physical distance to bounce off the ceiling, floor, and walls before reaching the listener. This delay is significant because while direct sound represents the audio accurately, reflected sound acts as a secondary, late-arriving signal that corrupts what the engineer hears. These initial bounces are classified as early reflections or first-order reflections. These are waves that strike exactly one roam boundary before reaching the ear. Because the travel distance is only slightly longer than the direct path, these first-order reflections arrive mere milliseconds after the primary signal. A specific version of this is loudspeaker cabinet edge diffraction. This happens when the sound wave wraps around and bounces off the physical corners of the speaker box itself. To eliminate this specific boundary discontinuity, designers often use flush mounting or soffit mounting, where the monitors are built into the front wall to create a continuous surface. Regardless of the source of the bounce, the problem remains the same. What happens mathematically when the pure direct sound and a slightly delayed early reflection occupy the same space? By allowing these reflections to persist, the room geometry forces two identical time-shifted signals to interfere with each other, degrading the accuracy of the audio. This interference is governed by linear superposition, the physical addition of the direct sound and the delayed early reflection at the listening position. This chart maps the result of that addition. On the bottom left is our direct sound wave, and beside it is the reflected wave, shifted slightly along the timeline. At frequencies where the path length difference is a perfect multiple of the wavelength, we get phase alignment. The waves add together in phase, creating resonant peaks that boost the volume by as much as 6 decibels. Conversely, at frequencies where the waves are 180 degrees out of phase, they cancel each other out. This phase opposition carves deep energy notches into the frequency response. This pattern of repeating peaks and valleys creates a shape resembling the teeth of a hair comb. This is a comb filter. Comb filtering makes it impossible to hear a flat frequency response. It adds a distinct coloration to the timbre of the sound, causing the engineer to hear cuts and boosts that aren't in the mix. These erratic phase shifts across the frequency spectrum also distort the accuracy of the stereo imaging, making it difficult to place instruments within the soundstage. The physical geometry of the room essentially removes specific frequencies from the signal before they ever reach the mixing engineer. The physics in the air is compounded by how the brain processes sound, which changes depending on the exact millisecond delay of the reflection. If we map human hearing on a timeline from 0 to 100 milliseconds, we can see the zones where reflections become problematic. The most critical window is the period between 0 and 5 milliseconds. Reflections arriving this early fall inside the critical bands of human hearing, causing significant smearing. Within this 5 millisecond window, the brain cannot distinguish the bounce from the source. It will pull the perceived center of the stereo image toward the reflection point, even if the reflection is very quiet. In contrast, reflections arriving between 20 and 40 milliseconds fall under the precedence or Haas effect. The brain integrates these into the primary sound, adding a sense of loudness and spaciousness without the destructive coloration. Reflections that arrive after 50 to 100 milliseconds are processed differently. The brain resolves these as distinct, distracting echoes. The primary objective in studio design is the total elimination of any reflected sound falling into that 0 to 5 millisecond window. Because the brain cannot untangle these earliest reflections from the true signal, they must be managed architecturally. Establishing a reflection-free zone, or RFC, at the mix position is the standard solution for these interference patterns. One approach is the soft option, which involves covering the entire front of the room in broad, porous fiberglass absorption. While total surface coverage eliminates early reflections, it also removes the room's natural energy. This results in an environment that is uncomfortably dead and fatiguing for the engineer. The hard option, or spot treatment, is the more precise alternative. This leaves walls untreated except for the specific points where first-order reflections bounce toward the listener. Acoustic accuracy is achieved by selectively targeting the destructive reflections while preserving enough energy for the room to sound natural. In high-end studio design, acousticians often avoid heavy absorption by using geometry to redirect sound. In these rooms, the front walls and ceiling are built at mathematically calculated splayed angles, rather than being parallel. These angles act like billiard cushions, deflecting early sound rays wide so they pass the engineer's ears and head toward the back of the room. Once redirected, these waves strike rear wall diffusers that scatter the energy back into the room to create a diffuse ambient field. For the stereo image to remain stable, the room must have a symmetrical six-sided RFC. Both speakers must interact with identical boundary shapes, or the phantom center will shift. This architectural approach focuses acoustic clarity at the mix desk while allowing the rest of the room to remain lively. Most home studios are rectangular, making the construction of splayed, geometric walls impractical. Create a localized reflection-free zone in any room using the mirror trick. An assistant slides a sidewall mirror. When the seated engineer sees the speaker's tweeter reflected, they stop. Since sound reflects like light, this visually marks the exact first-order reflection point. Centering a 2x2-foot fiberglass panel on this mark neutralizes the comb filtering threat for that specific boundary. Accurate audio mixing depends on this type of microscopic timeline management, utilizing the physics of the space to achieve a transparent listening environment.